Technical deep dive on API design fundamentals, REST versus GraphQL versus gRPC. Welcome to our technical deep dive into the fascinating world of API design. The way we build and connect software has fundamentally changed, moving far beyond simple data exchange to power complex distributed systems. Choosing the right API style is no longer a minor detail. It's a strategic architectural decision that impacts everything from performance and scalability to developer experience and long-term maintainability. In the diagram titled Strategic API Architectural Choice, you can see just how critical this decision is for your entire application ecosystem. Today, we're going to explore the three dominant API paradigms: REST, GraphQL, and gRPC. We'll dissect their core tenets, practical implementations, and how they truly stand up in production. As illustrated in our API design paradigms, REST, GraphQL, gRPC diagram, each offers a distinct approach to building robust and efficient systems. Let's begin with the ubiquitous standard, REST, or Representational State Transfer. Conceptualized by Roy Fielding in 2000, REST is an architectural style, not a protocol. Its widespread adoption stems from its simplicity, statelessness, and reliance on existing, well-understood web standards, primarily HTTP. Our REST ubiquitous architectural style diagram highlights its foundational role in modern web development. REST is built on several core principles. First, client-server separation. This strict division, which you can visualize in the client-server separation of concerns diagram, means the client handles the user interface while the server manages data and application state. This enhances portability and scalability. Next, statelessness. Each request from client to server must contain all necessary information. The server doesn't store any client context between requests. This simplifies server design and improves reliability, making horizontal scaling easier. The stateless API interactions visual clearly depicts this principle. Third, cacheable. Responses can be explicitly labeled as cacheable, allowing clients, intermediaries, or the server itself to reuse data. This significantly reduces latency and network load, as shown in the cacheable responses for efficiency diagram. Then, we have a layered system. Clients generally don't know if they're connected directly to the end server or an intermediary. This allows proxies, load balancers, or gateways to be introduced to enhance scalability, security, and performance without affecting the client. Take a look at the layered system architecture diagram. Finally, and most crucially, the uniform interface. This defines how clients and servers interact. The uniform interface principle diagram illustrates its central role in REST. It consists of four subconstraints. First, resource identification. Resources are identified using URIs, like /users/123. Our resource identification with URIs diagram provides clear examples. Second, resource manipulation through representations. Clients interact with resources using representations, typically JSON or XML, in the request body. Third, self-descriptive messages. Each message includes enough information to describe how to process it using HTTP methods, headers, and status codes. This is clearly shown in the self-descriptive API messages visual. And fourth, hypermedia as the engine of application state, or HADIOS. This suggests clients should navigate the API entirely through links provided in the server's responses. While an ideal, HADIOS, depicted in the HADIOS, hypermedia as the engine of application state diagram, is often the least implemented constraint in practice due to its added complexity. REST APIs are truly the workhorse of the internet. They power almost all major public APIs like GitHub and Stripe, and are fundamental to web applications, especially those built with single-page application frameworks. The REST for Public APIs and Web Applications diagram perfectly illustrates their widespread applicability. In practice, REST excels in defining resources as nouns, not verbs. You use HTTP methods like GET for retrieval, POST for creation, PUT for complete updates, DELETE for removal, and PATCH for partial updates. Understanding idempotency, that making the same request multiple times has the same effect as making it once, is crucial for robust error handling. Correct HTTP status codes are paramount for self-descriptive messages: 200s for success, 400s for client errors, and 500s for server errors. Versioning, often via URIs like v1/users, is critical as APIs evolve. Pagination, filtering, and sorting are typically handled through query parameters. However, REST does have challenges. Clients often receive more data than they need, known as overfetching, or need multiple requests to get all data, which is underfetching. This leads to inefficiency, especially for complex user interfaces. There's also a lack of strong typing by default with JSON, which can lead to runtime errors if contracts are not strictly enforced through documentation like OpenAPI. Despite these, REST's enduring popularity is due to its simplicity, reliance on existing HTTP infrastructure, and broad tooling support. It excels where resources are well-defined and a broad range of consumers need to interact. Now let's shift our focus to GraphQL, the client-driven query language. Developed by Facebook in 2012 and open-sourced in 2015, GraphQL fundamentally shifts control over data fetching from the server to the client. It's a query language for APIs and a runtime for fulfilling those queries. Its most defining feature is ask for what you need, get exactly that. Clients specify precisely the data structure and fields they require, eliminating overfetching and underfetching. It's also hierarchical, meaning queries mirror the structure of the data they return. Crucially, GraphQL has a strong typed system. Every API is defined by a schema in GraphQL Schema Definition Language, or SDL. This schema defines all possible data types, fields, and operations, queries, mutations, and subscriptions, providing strong guarantees about data shape. Unlike REST with multiple endpoints, a GraphQL API typically exposes a single endpoint, usually /GraphQL, where all operations are sent, and introspection allows clients to dynamically discover the API's capabilities by querying the schema itself. GraphQL shines in scenarios where data requirements are dynamic and varied. This includes complex user interfaces, especially mobile apps needing optimized data payloads, and aggregating data from multiple microservices or backends, where a GraphQL server acts as an API gateway. It's also great for rapid prototyping. Schema design is the heart of a GraphQL API. You define object types, scalar types, queries for read operations, and mutations for write operations. Subscriptions enable real-time data push, typically over WebSockets. For every field in the schema, there's a corresponding resolver function on the server responsible for fetching that data from its underlying source. A common performance pitfall, the N+1 problem, occurs when fetching related data. Data loaders are a critical optimization, batching requests to reduce database queries. Error handling in GraphQL differs from REST. A GraphQL server typically returns a 200 OK status, even with logical errors. Errors are included in a top-level errors array in the JSON response payload, requiring clients to explicitly check for them. Caching is also different. Client-side libraries like Apollo Client provide sophisticated normalized caching, a significant advantage. Server-side caching is more challenging due to dynamic queries, requiring application-level logic rather than traditional HTTP caching. GraphQL's advantages include eliminating overfetching and underfetching, fewer round trips, strong typing, and excellent developer experience with tools like GraphQL. However, it can increase server complexity. Caching is harder on the server, and file uploads can be awkward. Rate limiting and performance monitoring are also more complex than with REST. GraphQL shines when clients have diverse and evolving data requirements, particularly in applications with rich user interfaces or when aggregating data from disparate backend services. Finally, let's explore gRPC, or Google Remote Procedure Call, the high-performance RPC framework. gRPC is an open-source, high-performance RPC framework developed by Google, designed for low-latency, high-throughput communication,